All right, so my name is Marc Saegesser, and tonight I'm going to try to answer the question, why Scala? Okay, so I actually first encountered Scala about 8 years ago, 2011, and there was something about the language that kind of drew me in. And then I got lucky, and I was actually able to use it for a real project at work right away, and I've been hooked ever since. So I've been a Scala programmer pretty much full-time since 2011. And it's actually been a really rewarding thing for me, right, both professionally and personally. So I'm a software developer. I still write code for a living, all right? And Scala has actually completely changed the way that I make software. And if I take a look back over the last 10 years of my career, you know, the things that I've been able to do, what I've learned, how I've grown as a developer, it's actually really hard for me to see how I could be where I am today without having had that experience of going through Scala. So that's what I want to try to share some of that with you all this evening, right? To try to hopefully present the language in a way that's approachable and also show what makes it different and powerful. Right. Now, I actually spent quite a bit of time trying to figure out, well, how do I approach this, right? Because the subject matter is huge, right? How do you take something as big as a language like Scala and try to condense it down into something that's digestible in a sitting, and yet still actually do justice to the language? Now, what I finally came up with this, I put kind of two constraints on myself to try to limit things down. And so the first is, I'm going to focus on like concrete examples, right? Real code. Right, so there won't be much in the way of theory or big hand-wavy ideas or anything like that. I'm going to actually show you real Scala code, how we actually do things in the language. And then the second thing is I'm going to try to limit myself to what I like to think of as mundane Scala or ordinary Scala. Right, so there won't be any type astronautics or fancy jargon or anything like that. So I'm going to stick to things that are really the bread and butter of Scala programming. So these are things that I actually use every day. Okay, so mundane here does not mean you dumb down or simplify or anything like that. This is basically just the core of the things that we use to write programs in Scala. Right, now I'll admit, okay, fair warning here, a lot of these mundane things are probably going to look kind of strange and confusing. All right, just know that going in. Right, but that's not actually because they're difficult or complicated or anything like that. Right, where this comes from is just because these things are new, they're unfamiliar, right? So you guys have all spent a lot of time learning how to recognize patterns in Java or C# or the other languages that you write in. And these are just new patterns, right? They're unfamiliar patterns. Your brain just hasn't learned to recognize them yet. So a lot of times you look at it, it almost looks like noise, right? So that's one of the things I want to try to accomplish tonight is to just show you some of these patterns, show you how they work, so that you'll be able to maybe start recognizing. So if you look at some Scala code in the future, you kind of have a better idea what's going on. Right, but even though these things might be, you know, mundane in some sense, right, they actually are still really powerful. Right, I think transformative. Right, I think the Scala language, you know, actually changes the way we think about making software. Right, so hopefully we'll be able to, you know, see some of that tonight. So here's kind of my plan. Here's the agenda. So what I want to do is kind of start off by just showing a little bit about the language, some simple examples. And then what I want to do is like really dive in. We're actually going to look at a real application, you know, how we actually use these things to solve problems in software. And then I want to change and talk a little bit about Scala's type system. Look at a little bit of, take a little tour of that. Because it's this type system, I think, that really distinguishes a language like Scala from the languages that you might be more familiar with. Right? And this type system really is a game changer. Okay, and then finally at the end, what I want to do is I want to step back and take a look at kind of a bigger picture, like get some perspective. Right? So this is a talk about Scala, but Scala is actually just kind of one small piece, right, of a much bigger thing. Right? So having seen a little bit about Scala, and what does that kind of tell us about this bigger picture, and maybe you know, what might be coming down the road in the future. All right, so that's the plan. So let's get started. All right, so first I think we need to answer the question, what is Scala? All right, now, Scala started as a JVM language back around 2004. And I don't think this is a crowd where I really need to explain why targeting the JVM might have been a good idea. It's a very powerful and efficient runtime. The asterisk there is because Scala is actually bigger than that now. So we have Scala.js, which is a JavaScript runtime for Scala. And there's even an experimental project now called Scala Native, where we can take Scala code and actually compile it down to platform-native executables. Right, so it's really grown over the years. But actually, none of that actually has anything to do with what I'm going to talk about tonight. Right? What I want to focus on tonight is what really makes Scala something different. So Scala is this kind of hybrid, multi-paradigm language. So what that means is Scala is an object-oriented programming language. And it is a functional programming language. It is actually both of these things at the same time. Right? And that actually makes Scala almost unique. I think OCaml is probably about the only other language that kind of sits in that space. So we kind of understand what this means. Now, one of the things I've noticed is that when people come to Scala, if they come in from like this pure FP side of things, they really kind of focus on just the FP and they want to ignore all the OO side of things. And then the other groups are people coming in from Java and C# and languages like that. Well, they want to focus on just the OO side of things and kind of shy away from all that newfangled FP stuff. I mean, they see, Scala as like, a better Java or Java without the semicolons or something like that. But I think both of those camps are actually kind of missing something important, right? To really effectively use the Scala language, you really have to embrace the fact that it is both an object-oriented language and a functional language. So hopefully what I show you tonight will try to help make that clear. So we're actually going to see things that are both SP and object-oriented. All right, so let's dig in. So I want to start by looking at some really simple Scala code. Really simple. All right, so we're going to do factorial. All right, and you're allowed to groan at this point. It's like, oh my God, it's actually doing factorial. All right, so the fact that it's factorial is actually completely beside the point here. The fact that it's factorial doesn't mean anything. The reason I use this, so I actually lifted this from Martin Odersky's book, Programming in Scala, because it's actually one of the smallest examples that I found that actually shows some of the things that are actually really different about Scala. All right, so let's just kind of walk through this and see what some of these things are. All right, so up at the top, so def is just a keyword. It says we're defining a function. The name of the function is factorial. And then we've got in parentheses our argument list, with nothing really surprising yet. And then here comes kind of the first wrinkle. So this x colon big ints. Right, so this is what's called a type annotation. So what this means is that x has type big ints. Okay, so in a language like Java, you're maybe used to seeing something like, type space name. Well, in Scala, we actually do it the other way around, right? It's name colon type. And that was not done just to change things and confuse people, all right? Where this actually comes from is Scala supports something called type inference, right? So there are times when we don't actually have to write down these type annotations. The compiler can just figure it out for us, right? And in those cases, we just leave off the type annotation. So this syntax here with this colon big int actually just makes it really convenient that the structure of your program, of your code, doesn't actually change. You just leave that off, and the parsing of the syntax is still the same. So that's where that comes from. So that's a type annotation. And again, at the end of, after our argument list, we have another one of these type annotations. So that's actually the return type of this method. Right, so factorial is a function from big ints to big ints. Now, big int is actually a class from Scala's standard library. And all it does is just kind of wraps Java's big integer class. So all this means is that these things are just arbitrarily sized integer values. That's all this is. All right, so then we have an equal sign that separates the function definition from the body. All right, and now things get weird. All right, so what's going on here? What is this kind of naked if thing hanging out there in the breeze? Okay, so this is what's called an expression. Right, and this is actually really important in Scala. Right, in Scala we have this distinction between expressions and statements. So an expression is something that we evaluate to get a value, right? And a statement is something that we execute for its side effects, right? So like a simple expression might be 1 plus 2, right? You evaluate 1 plus 2 and you get a value 3, right? In Scala, it turns out if is also an expression. So we evaluate this if, and we're going to get a value. And now it also turns out that function bodies in Scala are expressions. So you notice there's no return here, right? So functions in Scala are expressions. So what's going to happen is here we evaluate this if expression, and then whatever value we get out of that will be the return of factorial, right? So you can kind of contrast that with, say, an if statement in a language like Java, right? So in Java, if you call if, you don't get a value back out, right? So the body of your if statement has to have some side effect, has to modify something else to actually have any sort of impact. Sure.
So a function by definition never has side.
So there's a distinction. What we're going to look at tonight are what are all called pure functions. So we don't have side effects. And that's actually a goal as we write this kind of FP stuff, is to try to avoid side effects. So all we'll see tonight are pure functions. All right, and this is obviously an instance of a pure function. Okay, so we're going to evaluate this if to get a value. So how do we evaluate if? Well, it's the way you would expect. So we're going to evaluate that first sub-expression, x equals 0. So if x is equal to 0, then we're going to evaluate the first sub-expression, which is just that literal 1. And if it's false, then we just do the second one after the else. So whichever one of the expressions we end up evaluating, that will be the value of our if expression and the result of this function. So that's an expression, right? And it turns out that almost everything we write in Scala ends up being expressions rather than statements. Right? So it may seem like a subtle distinction right now, but maybe it'll make more sense as we keep going. All right, now there's some other kind of strange things going on here. So for example, so x is a big int, but we're doing this equality comparison with this literal 0. So what the heck is that? And the return value of this thing is supposed to be a big int, but that first expression evaluates to be the literal 1. All right? And then what about x minus 1? So x is a big int. How can we subtract this literal 1 from this big int thing? So I think there's some strange stuff going on here. Right? And what's actually happening, there's kind of two important concepts. So first, it turns out that these literals, 0 and 1, for example, are actually objects. Right? These are actually instances of the class int, capital INT. So in Scala, we actually don't have anything like primitive data types in Java. So this distinction between int and integer, right? In Scala, everything is an object, right? So because these things are objects, that first equality comparison there is an object equality. So this is going to end up calling an equals method on some class, right? So everything ends up calling equals because everything is objects. So this ends up being the equals of big ints. Right? And big int knows how to do numeric equality with things like ints and longs and things like that. So that works out just because big int is doing this object comparison. So what about this 1? What's going on there? So this is an example of what's called an implicit conversion. Right? So the big integer class defines some methods that basically say, if you have an int and you need a big int, I have a function that does that for you. Right? And if you have a long and you need a big int, there's a function that will do that for you. And these are put into what's called implicit scope, and the compiler just finds these things. It does that conversion for us automatically. So we can write just this literal ints, and the compiler will lift that up into a big int for us. All right, and then the next thing that's interesting here is, so this minus sign, for example, or the multiplication sign as well. So how do we do that? Well, the first thing that happens is there's another one of these implicit conversions that's going to turn that int up into a big int. But then this minus thing is actually not an operator built into the language. Okay? Scala actually has very few built-in operators. What this actually is, the multiplication and subtraction are actually methods. Right? They're methods that are defined, in this case, on big ints. So if you were to open up the source code for big int, you would actually see, a def with minus sign and then, argument list that just takes, another big int. So what's happening here is this syntax is actually just the same thing as having said x dot minus and in parens 1. So invoke the minus method on big int, passing it the parameter 1. Well, Scala just gives us this convenient syntax where we can take these types of functions and write them so that they look like an operator would be in another language. And that actually, what this does is gives us a lot of flexibility, right? A way that we can kind of expand the language in a way that's consistent. So we can add third-party libraries that use these same types of constructs, and it looks like they're adding things to the language that are the same way they work in the standard library. Right? So it's a way to kind of grow the language over time in a way that's consistent. We're not worried about strange operator overloading rules or things like that. There are no operators. It's just functions. And so what does that give us? Right? What's the value of all that? Right? And I think one of the ways you can see the value here is I'm going to compare it with the Java implementation of this same function. Right? And I think one of the first things that jumps out at you is that the Scala version is a lot smaller. Right? One of the things that generally happens is our Scala code ends up being much more concise than the equivalent Java code. Right? All those features that we talked about with the implicit stuff and everything, it just helps us write code that's more concise. And being more concise means that our algorithm is actually much more readily visible. Right? It's a lot easier to see what that code actually means than it is something like this. Okay, and so that'll be a recurring theme, the fact that we write much more concise code in Scala. Yeah? I would guess pretty close. Actually, I've never actually checked, but yeah, their behavior is certainly identical. Whether they're the identical bytecode or not, I'm not sure. Yes, one more. Actually, for this case, no, I don't need to report anything because the big N class is just, there's a standard set of things that are always available in your Scala source code, and that just happens to be one of them. But we do have import statements where we need to import various modules. That it just turns out in this case we don't need one. All right, so again, this was a really simple example. So what I want to do now, actually, in passing, I want to talk about this. So Growing a Language by Guy Steele. This is a fantastic presentation. Everybody should just go watch this. This is where Guy Steele is talking about these ideas, right, of a small language that we can dynamically grow into a bigger one. And these things were definitely on Martin Odersky's mind as he was forming Scala. So everyone should go watch this. A wonderful presentation. Okay, so now I said we were going to talk about a real-world program. See, actually, how we do something for real in Scala. All right, but the real world is boring. All right, so let's do a puzzle instead. All right, puzzles are fun. Okay, so this is cool. This is actually a homework assignment from CS 370, Creative Problem Solving and Team Programming. So this is actually from the Stevens Institute of Technology, which is out in Hoboken. So my son was a CS major here. He's now graduated. He's employed. He's on his own now, so yay. But one of the cool things about having a CS major for a kid is that every now and again he sends me his homework assignments just because he thinks I'll get a kick out of him. All right? And he's usually right. This was a lot of fun. I had a lot of fun with this thing. So you can probably kind of get an idea what's going to happen here. So we want to find solutions to this puzzle, where solutions means we can rearrange the tiles and rotate them. And we want all the adjacent sides to have the same color, but opposite ends of this shape. So we've got arrowheads and arrow tails. All right, so that's a solution. Now, we want to find all of the solutions that are unique up to rotation, right? So if we take this puzzle and move it 90 degrees, that would look like a new solution, but it's really the same one, just rotated. And so the instructions here is we only want to, report one of them instead of all four. So we either need to find a way to filter out the ones that we don't want, or better yet, avoid finding them in the first place. Okay, so how do you solve something like this? In any language, how do you approach a problem like this? Well, I think usually it's a good place to start with the domain model. Right? So what are the things that we need to be able to talk about and manipulate to solve a puzzle like this? Well, there are some obvious ones, right? We need a board, right? A board is going to contain tiles. It's going to have to be able to, the location of all the tiles and their orientation. We need tiles, obviously. Tiles have a label and they have edges. Then edges have colors and shapes, right? So that's kind of the data stuff we'll be thinking about. Another thing we might need is constraints, right? Some way to represent, given the location of the board, what are the constraints that apply to any tile that we want to put there, right? So that'll be another thing as part of our domain model, the concept of constraints. Okay, and then how do we solve the problem? What's the algorithm? Okay, so what I came up with, my solution, was you're going to start with, say, an empty board and like a bag of 3 tiles. And then the core algorithm is you give me a board and the tiles, and I'm going to give you back all of the legal boards that you can get to, starting from here and placing one more tile. So I'm going to fix tiles in place one by one. So you give me a board, I give you back potentially several boards that you can get to from here. Right, and then you just keep doing that over and over again. Right, so collect up all the things I got from the first round, feed them back in again. Right, now you're going to get back boards that have 2 tiles in place. We'll just keep doing this over and over again. And what'll end up happening is we'll get to a board that has no more free tiles, in which case we found a solution, or we get a board where I can't actually put a tile in that spot, right? There are no valid tiles that fit there. So now we found a dead end, right? There are no boards we can get to from here. So we just stop going down the search path. Okay, so that's it. That's basically the algorithm. Okay? So let's actually look at how we implement one of these kind of domain objects. And what I want to focus on is tile. Right? And again, I have to apologize for this slide. There's way too much code on this slide. So please don't try to read this. All right? In fact, all of the code that I'm going to kind of talk about here tonight, what I want to focus on is not the details of the code, the specifics of the syntax. What I want to do is kind of show shapes and patterns. So all I want to do here is just kind of show you the shape of what's going on, and then we're going to wipe most of this away. So what's happening here is up at the top, we're defining this trait called tile. Now, in Scala, traits are kind of this weird kind of thing that sort of like interfaces and abstract classes in Java. So the way to think about this one here is just think about it as an abstract base class. All right? So it has several things that are abstract that we're going to have to provide in our implementations. And it has some code that's actually going to be shared commonly across all of these instances. And then we have two implementations, or two instances of tile. And again, you'll see, so we have a class free tile that extends tile, fixed tile, which extends tile. So this is just the standard inheritance model that you're used to from a language like Java, right? So free tile is a tile, fixed tile is a tile. It's just that is a relationship. And that's really about it. That's really all I want to show for the shape of this. So what we're going to do is kind of dig in and focus on how we actually implement this particular class, a free tile. And the terminology I'm using here, a free tile you can think of as being in that bag of tiles I haven't placed yet. But I'm actually keeping all of them on the same board. It makes the bookkeeping easier. Right? So a board contains a combination of free tiles and fixed tiles. And a free tile does not impose any constraints on anything around it. It's just kind of taking up space. And a fixed tile has actually been put into a location on the board. And if you put another fixed tile next to it, you're going to have to satisfy the constraint. It just made the bookkeeping easier. So that's what these things are. All right, so the first thing that might jump out at you is this definition of free tile kind of looks like a function. And it is actually a function. This is actually the constructor of free tile. Right, so when we construct one of these free tiles, we have to give it a label and edges. Edges is another one of these domain classes that I'm not going to go into all the details on this. It's the obvious things you would expect to show, you know, top, left, right, bottom, sides, and colors and things. So initialize one of these things with labels and edges. And you'll have to take my word for it here. By virtue of being a case class and having these things named appropriately, that actually satisfies my need for having to define those label and edges values in my trait. Okay, so now let's look at this next thing here. So val rotations. So this is an example of like a member variable in this class, right? Now variable is kind of a bad name for it. So in Scala we have this distinction between variables and values, a var and val. So a var is like a regular variable in any other language. You can keep assigning to it over and over and over again. A val is something, it's different. A val, we assign a value when we first initialize it, when it first gets created. And once it's been initialized, we're never allowed to write to it again, right? So it's immutable. Once you've initialized it, it's fixed. I can't assign another value to it. If I tried to, it would be a compiler error. So here's how do we initialize this thing. So first you notice there's a type annotation here. So this rotations thing is going to be a vector of fixed tiles. All right, so I start with edges. So edges is this thing that we got in our constructor. There's a method defined on edges called rotation. What that does is returns a vector of new edges. All right, so what it's going to do is just give me all of the unique rotations of this given edges and return them back in a vector. Unique here, so if there was symmetry, right? So if it was, you know, we rotated the tile twice and it was the same as it started, right? We don't need to include that, right? Because that would just end up giving us duplicate solutions. All right, so edges.rotations is a vector of edges. Now we call map. Okay, so map is a method that's defined on vector, and actually on all of the other Scala collections. It's actually a really common thing. So map is an example of something that's called a higher order function, right? So it's a function that takes a function as a parameter. So in this FP way of doing things, functions become kind of first-class citizens. right? We can assign functions to values, we can pass them as arguments, we can return them. So this is a higher order function that takes a method as its argument. And the method here is actually a lambda expression, right? So that's a function. We'll dig into that in just a minute. So what does map do? What's its purpose? So what map does is it takes the set of elements that are in my initial vector, and it applies that function to each one of those elements. And what I get back is a brand new vector whose elements are, the result of having applied that function to all of those elements. Right? So map is kind of a way of doing transformations. Right? We're transforming a vector of one type into a vector of another type. Right? And this is actually a fundamental pattern in this functional programming way of doing things, is that we're transforming inputs into outputs using functions. So in this case, the functions, we're using our map and this function that we're giving map. Right? So we'll see this over and over again. This is a fundamental pattern of computing via transformations. All right, so now let's take a look at this, this lambda expression here. Okay, so R is the argument to this function. All right, and you'll notice here's our first example of type inference. You notice I didn't put a type annotation on this parameter, right? Because it's perfectly clear to the compiler that we're calling map on a vector of edges, right? So the function we're mapping over that better be a function that takes edges as its parameter. So it can figure out what that is. And in fact, this is an example. This is a really idiomatic way of using type inference. It would actually be kind of strange looking Scala to put a type annotation in there, because it's just clear from the context kind of what's going on. All right, so R is our argument. It's going to be a value of edges. And then the body is on the other side of this arrow. The body of this function is really trivial, right? I'm just calling the constructor for fixed tile. Right, and I'm calling it with our original label and just whatever these new rotations of edges that we got back. So what I'm doing here is basically kind of pre-computing all of the tiles that I could get to by rotating my input edges. And I'm storing away in this value just so I don't have to keep recomputing them over and over again. So that's all this is. It's a member value that's just storing this pre-computed data. So now let's look at with constraint. This is the other thing that we had to implement as part of being a tile. Right, so this is another function. It takes constraints as its inputs. That was, again, one of those domain objects we were talking about, something that says, what constraints do we have to satisfy for this case? And so the way this is done in Scala is, so rotations, again, it's a vector of fixed tiles. Filter is a method that's defined on vector, right? And filter is another one of these higher order functions, right? It's a function that takes a function as a parameter. And in this case, it's like a predicate function, right? It returns true or false. So what this is going to do is it's going to apply this predicate function to all of the elements in our list, or in our vector in this case. And what will result is a brand new vector that only contains the values where this function returns true. We're filtering out just the things that match this predicate. So that's what filter does. And again, you can see this pattern, right, of transforming inputs to outputs using functions. Okay? And this happens to just be another way of writing a lambda expression. It just says my argument. I don't have to bother giving it a name. So there are actually lots of ways of specifying lambdas in Scala. Okay, so let's actually step back a little bit and think about how would you implement these things in Java? Right? How would we do things like this map thing, for example? Well, what we probably do is, so we're starting with a vector, and we need to make a new one. You probably allocate an empty vector, and then you do like a for loop, right? You'd iterate over all the values in this vector, make this new tile, and then you would just modify that vector that you created, add these new things to it. Right? And filter's kind of the same way. You're starting with a vector. You want to make a new one, so we're going to make like an empty vector, iterate over all of these items, call this predicate function, and just add the ones that match into your new vector. Right? So these things are loops. Right? Map and filter are loops. So what we've actually done here is we've taken this really ubiquitous programming design, right? This idea of looping, iterating, and we've lifted it up inside our data types. So things like map and filter and reduce and fold and things like this. Right? What we're doing is lifting up this ubiquitous programming task into our data types. So this is really kind of fundamental. Right? This is one of the things that we do in these FP-style languages, is things that would be kind of normally things you would have to write out by hand in a language, are actually just done in this FP way using functions. So this is like control flow. This is looping, right? It's baked into functions. So the behavior of this loop is specified just by the function that I pass into map, right? So that's a really powerful concept, right? Because what we get out of this is that, again, this is very concise, right? I didn't have to go write out by hand all of this looping stuff. There's a lot less boilerplate, a lot less kind of scaffolding code around the edges. So again, this concise code lets us really express our algorithm, right? It's pretty clear to see what this does. Well, I say clear to someone who's familiar with the patterns, right? But it's pretty clear to me that all I'm doing is I'm mapping. So I'm transforming one thing to another. I'm filtering. I'm just extracting the things that I'm interested in. So this concise code really helps us express our algorithms in a way that's very clear. Okay, so that's enough of that. So, okay, this is actually the last slide on this topic. And this is another one that probably looks a little noisy to you when you see it the first time. All right, and again, that's because it's kind of an unfamiliar pattern, but it's actually the same pattern that we just saw on the last slide. Okay, it's going to be the same idea of the fact that we're trying to transform inputs to outputs using functions. And it turns out most of the code here are actually functions. These are most all lambda expressions. All right, so just in general, what's going on here is we're asking the board for its list of free tiles. Just give us the first free tile if you have one. All right. And that ends up being our target, right? So that's our target spot. And then what we're going to do is go through all of our remaining free tiles, kind of swap them into place, and see if any of those rotations actually match our constraints. And those are the ones we want to keep. Right? So that's what's going on here, right? I asked, do you have a free tile? Great, give me the first one. Pull out the constraints for that particular location. And now we're seeing the same pattern again, starting with free tiles called map. Transform this into something else. And we're transforming it into something that's actually another vector. We're calling that with constraint that we had on the previous slide. So that's going to be all the tiles that actually, match these constraints. And now I'm doing a filter. So a filter not here is just the inverse of filter, right? So things that return false rather than things that return true. And I'm not going to talk about all the crap that's in here because that's actually our ugly business logic. Okay, this is the thing that's actually trying to keep us from finding all of these duplicates. There's actually some really neat stuff in here, but we don't need to worry about it. But again, we did map and we did filter. And now at the end, we're going to do another one of these mapping operations, another one of these transformations. So we're going to take the tiles that were left after all of these other things and use them to build up new boards. So that's what this last map does. And it's a flat map because we would have ended up with a vector of vectors, and flat map just kind of squishes that down into just one level of vector. And that's it. Right? So that is the core algorithm of this whole thing. And it comfortably fits on a slide. Right? So we have this really concise code that actually expresses what is a fairly interesting algorithm and not very much code. Right? Now, again, it's probably a little bit noisy if you're not familiar with looking at it. But once you see the patterns, it's actually fairly straightforward. Okay, so you might be saying, okay, yeah, that's kind of cute. Maybe that's neat. So how does it work? Is it any good? How does it perform? All right, so here's where it turns out this homework assignment, the team that submitted the fastest code, solved the code the fastest, got some extra credit points. Okay, now, first off, that pisses me off. All right, that is a horrible lesson to be teaching, the next generation of software developers. That raw execution speed is the most, that's what gives you bonus points. Like, no, we want code that is correct and code that is maintainable. Execution speed is like one of the last things we care about, right? It needs to be just fast enough. All right, so I have to stop or I will rant. So this is why I can't be a professor. All right, so how does this perform? So it turns out that the team that got these extra credit points, you will not be shocked by this, wrote their solution in C. Okay, it had to. Now, they did learn an interesting lesson, though. What they learned was that malloc and free are actually really expensive, right? So what they learned is that their memory allocation was their bottleneck. Okay, so what they did, right, what C programmers have always done, is write their own memory allocator, right? So this is where we should have the conversation about intrinsic complexity and extrinsic complexity, but that's a different talk. All right, so they wrote their own memory allocator. And it turns out that after they did that, they solved puzzles at about 2 milliseconds per puzzle, which is, I actually don't know exactly what that number means. I don't know how they did their testing, but it's a number, so 2 milliseconds. So it turns out that my solution, written in idiomatic Scala, with all these nice fancy domain model things and all this stuff, so my code does it in 3 milliseconds. All right, so right off the bat, and I did not do any kind of optimization. All right, I didn't rewrite any code in any fancy way. All right, I wrote idiomatic Scala. Right, and I got, I think, within spitting distance of this hand-optimized C code. Right, so one of the first things we see is that, one, the JVM is not slow. Right, the JVM is actually a really performant platform. Right. The other thing I think we can see is that this FP style of doing things is in itself not necessarily slow. Okay. Now, I will admit it's not free. So one of the things is we usually end up paying a price of some extra garbage along the way. Right? But it turns out that JVM is actually really good at dealing with short-lived garbage. Right? So by and large, the Scala code actually performs pretty well. Okay? And which would you rather try to maintain? Somebody's handwritten memory allocator, or this Scala code that may look unfamiliar to it, but hey, at least I've got some property-based unit tests and I've got domain model stuff, right? So that's what's important. All right, but some of you guys right now may be kind of sitting on your hands, like, but. So this thing is a textbook, literally a textbook example of an algorithm that can be done in parallel. All right, so all of this exploring of this search space, all of these different tracking down these boards, all right, they're all independent of each other. We can do all of this stuff in parallel. So can we actually do that? Well, the Scala Standard Library actually has some parallel versions of many of its collections, one of them being vector. So I can actually just call .par on a vector, and I'll get back a new vector that has this parallel implementation. So what that means is things like map and flat map and filter, you kind of farm all their stuff out to an execution context to gather everything up at the end. So that's what I did. The only change that I made to my code was the level of software above this that keeps track of all of these boards and keeps calling this thing. I added .par. I literally pushed a button, right? And what I got out of it was a parallel implementation of this algorithm, right? And what happens then is if I run this on my laptop, it has 8 cores. And so if I look at it, it lights up all 8 cores. Right? Each one is about 85% utilization because there's still quite a bit of sequential code that's left in here. But, 8 cores, 85%. That's pretty good.
You control the amount of parallelism?
Not in that model. It's just, it uses, it looks at how many cores you have and scales that way, and you don't really have any input on it. So it's not, it's an interesting thing to try things out, but it's probably not, if you really wanted to get into it for real, it's probably not how you do it. What's that? Well, so this particular algorithm or the parallel stuff? Oh, sure, you could, it would be interesting. Go try to do this. So you've actually seen the solution now. Right? Go try to do this in Java and see what the code looks like and compare it. So you would not be able to do this FP style of things, right? But the algorithm could be done in Java. It's an interesting experiment to go see what these two things look like side by side. Okay, so anyway, so I've got this, parallel implementation running that I got pretty much for free. And it turns out that it now solves these puzzles in 2 milliseconds. So I got like a 33% improvement in throughput by pushing a button, right? And the reason I can do that, the reason it's actually safe for me to do that simple transformation is because if you noticed, all of those domain objects that I showed are actually immutable, right? So once they've been created, they cannot be modified. So it's safe for me to throw this thing out here. So all of these boards are actually referencing the same set of tiles all over the place. There are hundreds, maybe thousands of them. And it's safe for me to do this without any locking or synchronization because all of my data is immutable. Right? So that's kind of one of the powers of this immutable data is that we can start doing concurrency very safely and efficiently. Okay, so I think that was really all I wanted to say about this. All right, so we've seen, again, this pattern of transformations, inputs to outputs using functions. And the fact that, again, these are a bunch of loops that, lifted up inside our data types. You know what to take away from this. All right, so here's where I wanted to shift in and start looking at Scala's type system. And the way I'm going to do that is with these three types, option, and either, and try. And the reason I chose these, well, first is these are kind of our mundane type. We use these all the time. And the other is that when people first kind of come to Scala and they find these things, they often get confused. Right? This is kind of a stumbling point for people that come to Scala. It confused me, actually, when I first started with Scala. And to be honest, that actually kind of ticked me off. Right? Because if you look at these data types, they're actually pretty straightforward. There's not a whole lot there. So it bugged me. Why was I being confused? Why did I not really get where I would use these things or how I would use them or what they were for? And what I finally learned, actually long after I had become comfortable with them, was that confusion comes from the fact that they're actually new. Right? These actually are data types that you can't actually represent in Java. Right? So these are types that you probably have never encountered before. And so the fact that they're new to you, that's where this confusion comes from. So what I want to be able to do tonight is part of kind of introducing these things is take some of that unfamiliarity away. Right? So that when you see these things in the future, maybe they'll make a little bit more sense to you. Okay, so option. The purpose of option. Option is a data type that we use to represent the presence or absence of a value. Right? That's it. That's all it's for. Presence or absence of a value. Okay, and the way we do this in Scala, it looks like this. So, and this is a pattern that we're going to see over and over again. All right, so we start with this sealed trait option. And this is actually the first time we've seen one of these type parameters. So this is like generics in Scala. Right? Only in Scala we have the more stately square brackets rather than the angle brackets in Java. Right? This is just generics like you've seen before. So we have an option of A. And the way we represent this in Scala is we have two instances, two implementations of this trait. One called sum, which contains a value of A inside of it, presence of a value of type A, and another implementation called none, which does not have an A inside of it. So sum represents the presence of a value A, and none represents no A. And so I've got a couple examples here, just assigning some option events. So I've got one that contains a 42, and one that's a negative value, and one that's none, one that represents I don't have a value of type A. Okay, so how do we use this now? So I'm actually going to show two functions on all of these data types. Right? These are basically the lowest level kind of building blocks, the things that we use for working with these data types. Right? And the first one is called map. So map is something that we've already seen before, right? It was transforming a vector from one type into another. And it's doing the same thing here. It's transforming an option of one type into an option of a new type. Right? And it does that by using this function. So this is the type signature of a function. So that's a type annotation. F is the name of the parameter. And it has type A to B. So A arrow B is a function from A to B. All right? And so I've shown you a couple examples here of how we would actually use that. So I'm mapping this toString function over int. So this is going to transform an option of int into an option of string. I'm just applying that function to it. Okay? So that's this thing. And again, we've kind of seen that before. So the next function I want to look at is called flat map. And I've rearranged the formatting here a little bit so you can really highlight the distinction between these two. So in map, we had a function from A to B. So you give me an A, I will give you a B. In flat map, this function type is you give me an A, and I might give you a B. Right? The return type has an option in it. So you give me an A, and I will give you back an option of B. Right? So this kind of represents a computation that may or may not be able to return a value. Okay? So we have two different styles going on here. You give me an A, I will definitely give you a B. That's map. You give me an A, I might give you a B. I'll give you an option of B. So that's flat map. Right? So two different types of computation. And again, I'm showing just some trivial examples down here how you might use flat map. So if it's greater than 0, I'll convert an int into a string, and if it's negative, I say I can't do that, right? So I turn this into a none. So what does it actually mean to map a function over none, or flat map a function over none? Well, you can actually kind of see this from the types, right? So these types are completely generic. I have no idea what a B is or what an A is. So I have no way to like create a B out of thin air. So the only way I can get something of type B in order to make an option B is because I already have an A and I have a function that knows how to make a B out of that. None is a type that says I don't have a value of type A. So the only thing you can legitimately do is nothing. Just return none. So when you map a function or flat map a function over a none, you get back none. Right? So that basically represents a computation that can no longer go forward. Okay, so that's it. That's really all we need to say about option. That's what option does. So one of the things you notice I did not say in any of that was that none represents error. Right? None just represents absence of a value. Right? So for example, Scala's future data type was a data type for representing asynchronous computation. If you ask a future for its value, it gives you back an option. And what none means is that, well, the answer is not here yet. I have no idea what the answer is. And if it actually has arrived, then we get a sum. Right? It's actually going to be the result of your computation. Right? So again, option does not mean, or none does not mean error. It just means no value. So it turns out that option is kind of a blunt tool in that regard. Right? Why did I not get a value? Right? And so that's where this next data type comes in. It's called either. So this is an example of a type that has two type constructors, right? A and B. Again, just generic types. So in this case, we have, again, two implementations. We have something called left, which is going to contain an A, and something called right, which is going to contain a B. Now, you might be asking, where did those names come from? All right. Well, if you notice, A is on the left, and B is on the right. So we have a left of A and a right of B. It is not my fault. That comes from Haskell. Right? So how do we use these things? Again, it's very similar to the stuff we saw before. So I'll just make a couple examples. One of the things to note about either is that the convention is that we use right to indicate kind of successful values, and we use left to kind of to mean errors. And the reason we do that convention, so this is why I'm using, so I have a right of 42 and a left of oops, right? This is my error message. The reason we do that is these functions, map and flat map, operate on type B. So they operate on types that are in the right rather than the left. Right? So the idea here is that we can use map and flat map to kind of proceed with this computation on successful values and just stop as soon as we come up with a left. Right? And so here are a couple examples of this. I'm not going to go through these, right, because they're the same things over and over again. Right? The only thing to notice here is that map, we have a function from B to C. You give me a B, I will definitely give you a C. Or we have, for flat map, you give me a B, I might be able to give you a C wrapped inside a right, or I might give you back a left with some error in it. And the goofiness with the type signature here just says that when we do that, that error, that thing we give you back on the left, is either the same type or a super type of the thing you started with. We're not allowed to like completely change the type that's inside that left. That's what that goofy syntax is. All right, and that's it. That's either. It's the same pattern over and over again. Right? And then finally, because that left is usually an error, Java gives us kind of this made-to-order class for representing errors. We have throwable. All right, so it's actually really common in real-world Scala code is to see an either of throwable and some type. Right. So the next thing is try. Right, is just kind of a convenience thing that we get in Scala. It's exactly like either, with a throwable on the left. So now again we have a trait try. Again, now it's back to just one type parameter. Right, and we either have a success of A, I successfully computed this value for you, or you get a failure with some throwable that just tells you, okay, this is why I didn't give you a value. And it's convenient because we have this kind of constructor type thing here where we can wrap some code inside a try, and it will automatically catch exceptions for us and turn that into a failure, or just give us a success if it worked. So again, the examples look just like you've seen. Okay, so I kept saying that I wanted to do real-world examples. None of this stuff has really been real-world. This is just kind of introductions to the type. So I actually want to show an example of how we would use this. All right? And so what I did is I tried to make the worst code that I could think of. All right, I pulled out all the stops on this one. So the idea here, which you probably can't figure out by looking at the code because it's so damn ugly. Right? So we have these three functions. Right? And this is a really trivial, a really made-up example. I'm going to ask for a database connection, right? And then if I get one of those, I want to, get user ID for name, which might give me back a user. And I'm going to use that to be able to like update an address in the database and get some confirmation code back that I can report to the caller. Right? And so this is an example. I've heard this called like the wedge of doom. Right? So I'm going to call this method. If it works, I go on and do the next one. If that works, I go on and do the next one. And so this is just riddled with null checks and magic numbers and sentinel values. And this is horrible. Right? But you will probably admit there's a lot of this stuff that's out there. All right? All right? This is everywhere. Okay, so there's all kinds of things that are wrong with it. All those magic values. The error handling, right, is way far away from where the errors actually happen. And I'm just really sorry for anybody who would have to like add a step in the middle of this. That would be horrible. So we want to do better. All right, so here's a way that we can do better using these types that we just saw. What I've done here is kind of the same methods, only now the return is an either. So in this case, I'm using an either of throwable. So get DB connection returns an either of throwable or my database connection. Right, so it can succeed, give me it back a right, or it can fail, give me a left. The same thing for all the others. Okay, so now how do we actually use this? Right, now you may have been thinking when I was talking about map and slat map and all these things, right, that's really cumbersome. It's ugly. I mean, you can see what they do, but it's really not very handy. So Scala actually gives us a new type of syntax. So this is called a for comprehension. So this is another expression. So we're going to evaluate this and get a value. And you might be able to kind of see what's going on here just by looking at it. So this first line here, so we're going to call this, get DB connection. If it returns a success, if I get back a right, so the for comprehension knows about the structure of these things that have map and flat map. So what it does is it uses that structure. So if I get back a right, it kind of reaches inside that right and binds this name C, to that successful value. So C here is an instance of a database connection. I successfully got a database connection. And then I can use that in the next step. I can call it get user ID for name using that connection. Right? And again, that may fail or it may succeed. If I get back a right, if I succeed, then I bind that successful value's name to you, my user. Right? So now you is a type user, or user ID. And so now I can use that in the next step in the computation, right? Which is calling updating, hopefully getting back a confirmation code. And then if everything works, what I'll end up with, the result type, and you can see it from the type annotation here, is I'm going to get back an either that is throwable or confirmation code because I'm yielding that result, my confirmation code.
So what's the difference with that arrow and
Oh, okay. So what this arrow means here, what this syntax does, is that's how we use this for comprehension to kind of do this magic thing where it can reach inside my right and bind a name to that thing that's inside. So this returns an either, but this is not an either. This is actually a database connection. And this arrow means that we're doing that operation. You can actually put equal signs in here, and that means you're actually just doing a raw computation. You're not doing one of these things inside of an either. Right, so that's what the arrows come from. It's just the syntax of the way for comprehensions work. So what this really is the happy path. Right? This is what the computation should do if everything works. And again, it's nice and concise. The algorithm, what we're trying to accomplish, is actually obvious from the code. So that's a huge benefit. Right? And all of the errors are actually happening. The thing here is errors become values. Okay? Errors are values that we return from our functions just like everything else. So we can't, for example, forget, right, or pretend to forget to handle an error, right? The errors are baked into our values. So what happens if something fails, right? So all these things are flat maps. Yeah, and we said as soon as we hit one of these failure cases, we hit a left, right, the computation stops. We can't really flat map over an error at this point. So what this actually ends up doing is we will get back a right with our successful value, our confirmation code, or we'll get back a left that has whatever the first failure that happened. All right? So again, this is very concise. We can't avoid handling errors. The algorithm becomes obvious. And actually, so this is using either, the code is the exact same shape if I switch to try. All right, so this kind of shows you kind of the power here. I mean, this is a pattern that shows up over and over and over again. Okay, so we've seen option and either and try. And so I made the statement earlier that these are types that you can't actually represent on the JVM. I'm going to kind of dig into that just a little bit here to kind of explain what's going on. So this is like the most furious bit of this entire thing. Okay, so these things like option and either and try. These are examples of something that are called sum types, S-U-M. All right, you'll also hear them referred to as like union types or disjoint unions. And the name comes from the fact that if you think about either, right, all of the either's are either a left or a right. We're just taking those two sets and unioning them together, kind of the sum of these things. All right, so these are the types that you can't actually represent in Java. Things that you can do, that you're all familiar with, like things like tuples and classes and records and things, these are called product types. Okay? And the name here comes from the fact that all the instances of these things are the Cartesian product of all of my, my constituent parts. So sum types and product types. Oops. So when we actually have a type system that has both of these things, both sum types and product types, then we have what's called an algebraic data type, or an ADT. Right? And this is the thing that is the game changer. This idea of having algebraic data type is what really separates Java or Scala's type system from Java. Right? And so one final example. This is the last example that I'm going to show. So I want to try to justify that claim, right? That these data types are really transformative. So I'm going to do this with one example. So this is a network client. This is actually one of the first things I wrote in Scala way back when, was this kind of network client. So this is actually a real example, although it's kind of simplified. So this network client, the kind of things you'd expect to be able to do. We're going to need a socket. We may need a heartbeat timer so we can exercise the connection, make sure it stays up. There may be some handshaking involved in doing a connection, so we might need a timer to keep track of that so like we can time out if it doesn't work. All these kind of things that you would expect. Now, if you think about this a little bit, you'll realize that we'll actually never have all of these things at the same time. Right? Most of these things, there will be cases where we have them or don't. So do we know any data types that we've seen that would represent the fact that we may or may not have something? Does anybody think about one? Option, exactly. Right? You're a genius, right? Because that's exactly the solution that I came up with right off the bat. So I did something like this. Right? So again, all of these things that I may or may not have are options. Right? So that's a step in the right direction, right? At least I'm saying that I may or may not have one of these. Yeah.
How is that different from in Java setting something else?
Okay.
That's a good question. Sorry.
It's a good question. I want to try not to get into it too much, but so null in Java, right, is a value. Right? It is an honest-to-God legitimate value. You are allowed to assign null to a variable. That's legitimate. Okay? What we're doing when we use null to represent absence of a value is purely a convention. We're saying, if I give you back a null, it means I didn't really give you anything. All right? But it's a convention that we can violate. There's nothing to stop me from, calling a method on null. All right? None, for example, is not the data type represents the fact that there is or isn't something here. We cannot ignore the fact that we may or may not have gotten something. Trying to operate on something that doesn't exist, we can't do it. Right? The data type, you can't map a function over none. Right? So the problem here is that we're just using this magic convention that none means not there. So there's nothing to tell me if I return none from a function or am I actually returning none from a function, right? I have to go and read the Java doc to find that out if they were nice enough to tell you, right? And then you have to have the discipline to always check that what you got back wasn't null. It's just a sentinel value. It literally is no different than the old COBOLers, right, using 9999 to represent a date, a year that doesn't exist, right? It's the exact same pattern, right? That's when they were nice enough to give us 4-year dates. All right, so anyway, so option represents, so we may or may not have some of these things. But there's a problem here. It's a perfectly valid instance of this class for me to have socket be none and heartbeat timer have a timer in it, right? I can make that an instance of a class that does that, right? But that's a bug, right? Having a heartbeat timer without a connection is not something we should ever do. It is unfortunately something that I did, right? My first implementation is way back when, is I had code that could shut down this connection and not clean up the heartbeat timer. It actually lasted for a long time before I actually discovered it. So there's something that's not that great about this code. So what we really want to be able to do is prevent ourselves from being stupid, right? Can we make a data type that will help us not do stupid things? And the idea here is this concept of make illegal state unrepresentable. Okay, and here's how we can do this. And we're going to go through this really fast. But so the idea now is it's the same pattern that we've seen before. This sealed trait connection state. All right, and now what I have are these 5 implementations of this that represent all of my states. Right, I could be disconnected or connecting or connected, yada, yada, yada. But now each one of these things only has the data that actually is valid for that particular state. So you notice that all the options are gone. Right, we've turned this into a type that no longer has any of these options in it. So now you could write something kind of like this. You can picture like a state machine where we're going from one state to another. Right, and now these data types, so one, they prevent me from making states that I shouldn't be able to make. Right, and they help direct my implementation. Right, when I have types like this, the appropriate thing to do becomes much more obvious. Right, they also help us maintain our code. Right, so if I were to add another state in here, all of these pattern matches are actually exhaustive. So if all of a sudden I had one that didn't cover one of these states, the compiler would yell at me. It would be a compiler warning. But if you're doing it right, warnings are errors, so it would fail. Right? So this helps us, yeah, okay. All right, so what this is helping us do is prevent making stupid mistakes. When I make the transition from connecting to connected, it tells me I can keep my socket, but I need to get rid of my connection timer, and I need to go make a heartbeat timer. Right? So again, make illegal state unrepresentable. Right? And I learned this technique from this presentation. So Yaron Minsky gave this talk on effective ML. ML here as in OCaml. So this is a talk that's actually about OCaml. The concepts are all the same. Right? And this is actually an excellent talk. Everybody should just go watch this. So this is where I learned this idea of make invalid state unrepresentable. And I went back and I re-implemented my network client, and the result was massively better. All right, so let's kind of wrap up. So why Scala? So what I tried to show here that there are kind of 2 new things that we get in Scala, in addition to the object-oriented stuff that we're used to. All right, we have this kind of rich and expressive type system, and we have this functional programming way of doing things, programming with functions. Right, and so I think what we've just kind of been talking about. So this rich type system lets us express rich domain models, right, that express the constraints of our business logic. The real-world constraints of our model are expressed in the types themselves. All right, so they help us from doing things that are stupid. These types help drive our development. Right, when you start working with these rich data types, what you find is it's kind of like putting Lego bricks together. When the types line up, right, then you're doing it right. When the types don't line up, it's telling you, you can't do, this is wrong, don't do this. Right, so these types really help direct us to how we should implement our code. And again, we talked about how it helps maintainability. And refactoring is actually really improved by this. So when you have correct code that has all of these types in it, and then you blow it up and re-implement all the stuff under the covers, and the types still confidence that you haven't really messed something up, right? It's the ability to refactor this stuff is really powerful. And again, we talked about error handling, right? Errors become values, right? And the fact that it's easier to kind of think about this because we get these concise representations, it's easier to see what our code does, right? They're functions, they're pure functions, inputs to outputs. We can test them easier. And this last one I think is actually really important, this idea of code reuse. Because everybody wants code reuse. And you will, if you start using things like these, immutable domain objects and pure functions, you will find new ways to reuse your code. But I think what's really important here, right, the code that we really get to reuse is the stuff that's been lifted up into our type system. Right? So it is almost absolutely a fact that anytime you write a for loop or a while loop in Java, you are re-implementing from scratch functionality that already exists in the Scala standard library. Right? I have not written a for loop in years. All right? So this is really important, right? Because the best way to improve our code is to not write it. All right? We get to reuse all of this functionality that's already baked into our types. Right? That's where we get these concise representations. That's where we get the fact that these algorithms become more apparent. Okay, so this is my experience over the last several years. Right? This is what I get out of Scala. Now, I would expect, though, that I have not convinced you. All right? And I should not have convinced you, right? Just listening to me blab for a while should not have convinced you that these rather bold claims are actually true. Okay? But what I hope I've done is that maybe kind of open a door a little bit, right? Crack the door open and kind of show that on the other side there's something different. There are some new things out there, right? Things you haven't seen before, things that might actually end up being powerful. Okay? And so that leads me into, I said I wanted to kind of wrap things up by trying to look at a bigger picture, to get some perspective. Right? So I said at the beginning that when I first started working in Scala, there was something that kind of drew me in to the language. And kind of looking back in hindsight, I understand what that was that as I was learning Scala, it was actually probably for the first time in maybe 20 years that I realized I was learning something new. Right? That I was actually learning something that I had never seen before. Right? So I've learned lots of different programming languages over the years, right? But none of them were actually a new paradigm. None of them actually changed the way that I thought about programming. Right? And Scala did that. Right? I was learning all of these new things. And honestly, it was thrilling. Right? To, after all this time, to actually be seeing something brand new. And it's still thrilling. I am still learning new things, years down the road. Right? So, I don't think we've actually, in our industry, has seen one of these kind of programming shifts in quite a while. Right? In fact, I think it probably goes back to the advent of C++, say in the mid to late 80s. Right? That was the last one I experienced, right? The transition to C++ style object-oriented programming. It's kind of the last paradigm shift that I think we've seen. If you look at the programming languages we have today, the major ones, they're really all the same paradigm, right? It's all imperative code and objects of some flavor or another. Right? So this was, I saw something new. I saw something outside of that paradigm. Right? So the fact that we haven't changed in a long time, right? I think one of the things that disturbs me more than that is that I routinely encounter people who seem to have a mission to prevent change. Right? I see all kinds of people like, no, we can't do that. No, none of that stuff. Won't do that around here. We know how to make software. That's not making software. This is the way we're going to do things. Right? But I think we've taken this paradigm, right, our object-oriented paradigm, and probably pushed it about as far as we can. Right? Complexity has caught up with us now. Right? It's time to start exploring new ideas. Right? Because what it turns out is that the status quo, this object-oriented paradigm that we're working, is really just kind of a small piece of something that's actually much bigger. Right? There's actually a whole new world out there that's just waiting to be explored. Okay? And the good thing is that now is a great time to start doing that exploration. We have all kinds of new languages that are showing up. Scala is one of them. Right? Scala lets us explore kind of these new ideas, new ways of doing things. But there are a lot of other things as well. Right? On the JVM, we have Ada, which is actually a hassle for the JVM, really. We have Clojure, right, which is another one of these JVM languages that explores different ways of doing functional programming. F# is a derivative of OCaml for the .NET environment. There are actually some really, really interesting languages in JavaScript, things like Elm and PureScript and TypeScript, that are exploring these ideas on the JavaScript runtime. There's all kinds of other stuff, Elixir, Unison, all kinds of things going on. And they're actually old languages, right? Things like Haskell and OCaml have been exploring this space for decades, right? And they're actually still rich and vibrant communities actually growing their languages today. Right? All kinds of stuff that we can learn from that. Erlang. Right? Erlang has been doing things for 30 years that your software can't do today. Right? So what can you learn from Erlang? Okay, so what I think we need is like this new culture of exploration. Right? We need to recognize that there are new things out there, right? New ideas that we can explore. And so that's what my challenge is for everyone here tonight. All right? Don't shy away from these new ideas. Right? Go track them down. See where they lead. Keep expanding your horizons. Right? In short, be explorers. Okay? So why Scala? Well, so Scala was my doorway that opened up that world. And so maybe it can be yours too. So, thank you. I know I've used a lot of time, but I'd be happy to answer some questions. I do want to, this is the photo slide. So all of the things that I referenced inside the talk are up here at the top, and the things down at the bottom are kind of future reading, good things to go explore. Okay, so question. Yeah.
Do you recommend
So here's what I'll say. As a brand new actual first language, brand new programmer, yeah, I think you could do Scala. Right, I do. I will bet that most of the people here disagree with that. Right? But the reason for that, right, is that all of us, myself included, we are at kind of a disadvantage, right? Because we bring a lot of baggage to the table, right? We've invested a lot of time and effort learning things like Java and C# and C++, right? Even if it was just unconscious, right? Some of you tonight probably thought, yeah, I know what software is, and yeah, that wasn't it, right? Because it's just, we're trained, right? We've spent time, as part of our identities, right, being able to program in these languages. And so when we see something that's brand new, right, there's a kind of a reaction against it. And I don't mean that we have to unlearn something in order to get here. We have to learn these new things. And we're at this disadvantage that we have to kind of push through. Right? So you'll get to a point trying to learn Scala, and you say, you know, if I just did this in Java, I'd be done. All right? We all go through that. Right? And the important thing is just to kind of recognize, you know, going in, I know that's going to happen. Sooner or later, I'm going to run up against one of these walls. And you just have to kind of push through. And when you get to the other side, it all makes sense. Right? Let's do this back over here. All right. Java's optional. All right, so this is my opinion. And I actually don't do a lot with Java 8, so I have not actually used Java's optional in Anchor. But I think the best thing I can say about it is that it was unfortunate. I think it was a mistake. And the reason I say that, which we talked about null checks, right? So it turns out that Java's optional is just a wrapper around a null check. All right? So there are things that we can't do with it, for one. Right? We should have, from the very beginning, been able to ask a hash map, does this key exist or not? We can't do that, right? Because it returns none if the key doesn't exist. And it also returns none, or it returns null if you stored that key in there with the value of null. Right? Ugh. So in Scala, map returns a none if the key doesn't exist, and then whatever value you actually put in there in a sum if you actually if the key is defined. All right, so right off the bat, it's nothing special. It's just a null check. But the thing that I think makes it really unfortunate is that you know, it's supposed to be this everybody's heard about, oh, there's option. There's this great thing, option, in all these languages. Oh, so now Java has it. And then you look at it and say, well, that's kind of dumb. Right? Ah, I knew it. Right? I knew those ST guys were all full of it. Right? So you get this thing that doesn't really give you a lot of extra value. And you can't use it the same way you would use option in Scala, right? Because we use option by doing things like map and flat map and for comprehensions and lambda expressions. Things that if you tried, some things you can't do in Java, and other things would just look really strange, right? So there's no really good idiomatic way to use it. And so again, I think the problem is people see it, realize it's kind of dumb, and then say that, oh, obviously all that other stuff they were saying is dumb as well. So that probably got me in trouble with a whole bunch of Java programmers, but you asked, so. All right, one more here. Go ahead.
I think I know.
I would like, I would, all right, go ahead.
And then what kind of app?
Anything in the world. It is a general purpose programming language. So I use it a lot for kind of back-end stuff, a lot of networking type of things. But honestly, you can do anything in the world. All right, so I mean, I've got an application I'm doing now, which is consuming Kafka streams, things like that. So it's doing some data manipulation. But it's a general purpose programming language. You can really do anything. So machine learning, I mean, that's an environment that I think is kind of settled on things like Python, for example. I'm sure there are ways of doing it, machine learning in Scala. I actually don't know. I'm not really much of an ML person. Well, so Spark. Yeah, so Spark is kind of a big data library that's written in Scala. I honestly don't have much experience with it. So I think there's another question back here. Hmm? Yep. Mm-hmm. Yeah. Okay. Yeah. There's, I think, a couple of ways to approach that. So one is the fact, remember, I talked about that domain model that we had. So that was really all object-oriented, right? Those things like tiles and boards and constraints and things, those were objects, right? They were maybe a slightly different style of object. So in object-oriented programming, right, objects are containers of data and behavior, right? We have internal state and we have functions to manipulate that internal state. And all of those things were the same way. They had internal state and they had functions. But if you look, the functions were a little bit different, right? There were no functions that modified any of that data. Everything was like just convenient ways of querying the data in a useful way, right? So I think, so these immutable domain objects, I think, are one of the best ways that we use the OO style of things in Scala. The other thing is, well, just one of the ways where we're using objects, we use them all the time in Scala. So things like vector or list or some of these other things, those are objects, right? So they contain data. So a vector has all of its elements. And then we have functions, you know, map and filter and reduce and things like that, that operate on that internal data. Right? So again, that's object-oriented. You compare that to something like Haskell, for example, which does not have classes. Right, so in Haskell, what you have are just data containers. So you have like a vector or a list. And then we still need to do these things, same things. We need to map functions over them, things like that. What you find there is the functions are all hanging off by themselves, and they take you know, a list or a vector or something as a parameter, and then operate over that. And in Scala, we're using this this object-oriented stuff where our data is now still buried inside objects, and we have methods that we call to manipulate that data. We still have this kind of, implied this in all of these objects. So we're still using that type of object-oriented. The other thing I'll say, I didn't want to dig into it in the talk, just because it's not super important. So you notice, so this is going back to this arrow puzzle thing. So you might have wondered, so this boards from thing, the thing, start with a board and give me new ones. So you might have thought, well, that might be a method on board, right? So here, start with a board and give me a bunch of new ones. But that's not how I did it here. So this is wrapped inside this other object, and there's another trait that defines this board builder type, of things that know how to build boards, and then a specific instance here. And the reason this is pulled out into something separate is that this is kind of our business logic type of thing. You think of this as kind of like a service, right? So we have our immutable domain objects, right, which have no real functionality inside them. They're just basically data. And then we have our service that takes these things and inputs and does something useful to them and makes outputs. So the reason you might want to split this out is, well, I had several different attempts at implementing this algorithm, trying out different things. Try them head to head, which things work better than the others. So I can have lots of different implementations of this kind of business logic. Whereas if I bake that into my objects, into my domain objects, then I have to start extending those and overriding things, and trying to get two things that you could compare head to head becomes a lot more difficult. And so this pattern that I have here, so these objects, you can kind of think of them as modules. Right, so one of the uses that we use, this kind of object-oriented style of doing things, is as kind of as a module system. Right, so you can take methods that are kind of related and group them together inside an object, and that kind of becomes a module that you can then pass around and use. But this is just a kind of an architectural technique. So did that come close?
Oh, yeah.
All right, thanks. Good.
So while you're on this slide, are there any common patterns that are used in the functional paradigm programming to kind of split things up, something like shareable aggregation? Like for functions like that, where you've got full page of stuff.
So these are all Lambda expressions that I just threw here into the code because, honestly, this is the way I think now. So it would probably be clearer if I pulled these Lambdas out into named functions and called them directly, as opposed to putting the Lambdas in here. And then you could create, so these might be things that you might want to reuse in several different places. So you just pull them out inside, say, another module object and just, call them there.
So I was thinking a little bit about social programming versus object orientation, and I was thinking, and I'm not sure if this is the correct term, but I was thinking about essentially storing functors by their return type in the models. That's I have a person model, it returns a list. So I would stick a bunch of functors that I was sharing, in a shareable aggregation file in the model as static.
Yeah, there are lots of different ways.
Is that something that's commonly done, or?
It doesn't really sound all that familiar to me, but again, there are lots of ways to use these techniques. And it's explore it, see how it works, see what happens. That's really the best way to answer it. Try it.
I have one more question. So you mentioned how easy it was to parallelize it. So I wonder, what if you have more complex problems such as gamified or solving a key transfer situation, where you have to communicate at least at the port? How do you deal with that?
Yeah, not like this. Yeah, this is really simple parallelism. All right, so Scala has some basic things built in, like a future data type, which lets you do some things in parallel and kind of, when this one completes, then move on and do the next thing, that type of thing. To do the kind of thing you're talking about, I think you really have to use kind of a third-party library. There is something that's just kind of coming on now called ZO, which is kind of a new kind of imagining of concurrency in Scala. It has some interesting things. It might do something like that. But I would expect you to have some sort of third-party library to do that for real. All right, a couple more questions.
So just, I'm trying to nutshell it in my head. Is it fair to say that Scala is the language I want to use if I want to have traditional object-oriented programming? I also want to have the ability to do functional programming? And is it true that the reason I want to do functional programming is probably difficult?
So one, Scala is a language that we use all the time.
So, in my opinion, if that were true, everybody would be using it.
Yeah. So, so there's learning curves to talk about as well. But it's kind of a hard. I'm not sure exactly the right way to go about answering.
Okay, so I'll concise it more. Why do I want? I get a couple of sentences. Why? So I'm a Java programmer, right?
Mm-hmm.
Or a C# programmer. Very familiar with object oriented. And I'm doing this for loop, as you mentioned.
Mm-hmm.
Sometimes I need to solve a for loop problem. Why should I switch to?
Again, I think I come back to that last slide. Right? I think you get the results we get. I think are much easier to understand. Again, once you've gone through the pattern, right? Our code is just as performant. We get all of the benefits of maintainability and type safety and things like that. So again, I just keep coming back to there are lots of reasons that the things that I think Scala brings to the table I think are really important, right? And there is a transition, right? And so you might think, well, when would I want to maybe try to think about this? And again, I would push back and say, well, it's a general purpose language. It can do all of these things, and it has all these benefits. So, for me, it's like, well, I just do it all in Scala. All right, there's a couple more here. Go ahead.
Just a comment on the last. Is that have Java out of the same.
Yep.
Is type safety, security, encouragement of still do a lot of stupid stuff.
Yeah.
But one of the things that these slides start to recognize code smell. A little bit. That's what it is.
Yeah, and one of the things that I just ran over real fast when I was what is Scala. So one of the benefits of Scala of being on the JVM is it has this really strong interop story between Java and Scala. So it's really easy to call Java code from Scala. Not quite as easy going the other way, but obviously you can do it. So it's kind of a way to kind of make a transition. So you can start with a Java code base and start maybe transitioning more towards Scala as you start bringing some of these new things in. Another thing I've seen people do is there's a lot of good tools for unit testing, for example, in Scala. Right, so people will, they might be a Java shop and that they can't actually put Scala into production, but they can use some of the testing tools in Scala to test their Java code, right? Because you can call Java directly from Scala without any problem. So you can start bringing it into your code base and the unit testing side, right, and kind of sneak it in. Anything else? I think we're getting kind of late, but one more maybe. Yeah, so actually, you know what's cool? I didn't say this, but it's actually a really neat thing. Okay, so remember we talked about there were some types and product types, right? And so if you think about this thing, so remember product types are like classes or tuples, right? So this connection state is a class, so it's a product type. But you notice that the things that are inside of it are options, right? Options are some types. So the type of this type is a product of sums, right? And if I look at this one, well, this is a sum type, right? Because I'm following this pattern, right? But each one of these things in the sum is a product. So what I have literally done, I have literally refactored this type from a product of sums to a sum of products. Right? Now, if that terminology tickles some brain cells that have been long dormant, right, that's because what you're seeing is this is just the tip of a much bigger structure. All right, so we literally just refactored a type from a product of sums to a sum of products. And that's, so getting rid of all these sum types, getting rid of all those nuns. So whenever you find yourself where you have this class that has like almost everything as an option, that's a smell. All right, that's telling you that there's one of these sum of products just trying to get out. Okay, last one, we're done. I really don't. So the question was Kotlin versus Scala. Scala. Yeah, I've heard that it's kind of missing something. So one of the knocks against Scala is that it can be kind of complex. There are actually lots of ways of doing the same thing, which means it's kind of hard to figure out which one you're supposed to do. There's been lots of ideas of kind of how to simplify things. I think maybe that's where Kotlin is going. But I have no experience with Kotlin. I can't comment. Okay, thank you all for showing up.